Today we are going to discuss about the phenomenon of electromagnetic induction. What is this electromagnetic induction? In short form it is called as EM induction. Before the early stages of the 19th century, most of the scientists and everyone thought that electric fields and magnetic fields both are separate. Before 19th century, electric field and magnetic field both are separated. That is their assumption, not true. But in the early ages or early years of the 19th century, Mr. Ørsted, he is the scientist, great scientist. He observed an accidental observation. What is that accidental observation? He placed one compass box needle like this. This is the magnetic compass box, which is placed near to a current carrying wire accidentally, unexpectedly. Means after doing some experiment, he just placed. Whenever this is a current carrying conductor, okay, like this, then he observed this magnetic compass box needle, it is simply vibrating or oscillating. And he moved this compass needle away from the current carrying conductor, then the deflections are reduced and the needle initially within a quick time it is coming to the rest position. So what is his observation? He concluded that a current carrying conducting wire produces a magnetic field. A current carrying conducting wire produces a magnetic field. Because of that only this magnetic compass needle is simply vibrating or oscillating. This theorem, this statement, later years it will become like this. A current or electric field which is varying with time or a varying electric field can produce a magnetic field. A time varying electric field can produce or easily produces magnetic field. This is the observation by the Ørsted, a great scientist. Then later, very next years of this discovery, most of the scientists including Ørsted thought like this: the converse effect also true or not? Converse effect means here time varying electric field is producing the magnetic field. Converse effect means a time varying magnetic field can produce the electric field or not. Most of the scientists thought about converse of this effect. What is the meaning of converse effect? A magnetic field, time varying magnetic field can produce electric field or not. But among them, Faraday, one of the great scientists, Michael Faraday, he was succeeded to prove the converse effect is true. And what is the experimental setup of him and what are the conclusions he made with respect to this induction phenomena. Now we are going to observe some experiments which are did by Faraday and Henry to prove the electromagnetic induction. The experiments did by Faraday and Mr. Henry These two scientists did the experiments to check the converse effect of the E to M, means electric field to magnetic field. So for that purpose, they took one coil like this. The two ends of the coil connected to galvanometer. There is a coil. In our textbook, it is given like a rounded shape. So it is very difficult to draw this rounded shape diagram in this 2D shape board. That's why let us assume the coil like this, which has some n number of turns. Now this coil is simply connected to galvanometer. Galvanometer is able to sense the small amounts of the currents and the direction of the current. Now take a magnet. They took one magnet of north and south poles. What they did, initially this conducting coil which is connected to the galvanometer and this magnet are separated by a finite distance. Now what they did, they moved this magnet towards the coil. Whenever the magnet which is at long distance, when it is moving towards the coil, what are the observations they experienced is, see this north pole which is acting like a high pole strength, south pole low pole strength. This north pole is able to attract the electrons which are inside the conducting loop. So therefore it creates the magnetic flux like this. And this flux is able to attract the conducting electrons which is in the conducting loop. Then they observed the deflection of the galvanometer needle towards the north pole of the magnet. Now they removed this north pole to the long distance. Then this galvanometer needle moved to the opposite direction. They did the same experiment with interchanging the poles of the magnet, south and north. And they have observed the same deflections in the opposite order or in the reverse order. So this is the coil connected to the galvanometer. One magnet is at a finite distance, which is at a distance. No change in the galvanometer needle. Now this magnet is simply approaching towards the coil. Whenever it is approaching, when they started to approach towards the coil, they have seen the deflections, and the deflection of the galvanometer is opposing the north pole of the magnet. Whenever they removed the north pole and moving the magnet away, then they observed the deflections in the opposite order, and while they interchanged the magnetic poles also, they have observed the deflections of the galvanometer in the reverse order. So this is one experiment did by Faraday and Henry with respect to magnet and coil. This experiment is also called self-induction experiment. Now, what is the reason for the deflection of the galvanometer needle in this experiment? Whenever the magnet is here, around the magnet we can expect a magnetic field. This magnetic field is nothing but a space surrounded around the magnet where another magnet can experience a magnetic force of attraction or repulsion. That is said to be magnetic field. Magnetic field is nothing but the content of the whole number of magnetic loops. That means this magnet is able to eject the magnetic field lines towards the conducting coil which is initially connected to the galvanometer. The number of field lines which is passing through unit surface area of the conducting body is said to be flux. The number of magnetic field lines passing through unit surface area of the body which is perpendicular to the plane is called magnetic flux. That means here some current is developed within the coil, and that current is able to oppose the magnetic flux, because flux direction is like this, galvanometer direction is also like this, which is opposing. This is the galvanometer deflection, this is flux. So what we can conclude from this experiment and what is the statement given by the Faraday and Henry after doing this experiment is a time varying magnetic field or the change in magnetic flux can create an induced EMF within the coil. A time varying magnetic field or change in magnetic flux produces an induced EMF in the coil. This is called electromagnetic induction. This phenomenon is called EM induction. They did the experiment with one magnet and one coil. Now they replaced the magnet with another coil. How that experiment and what is the result? We will see now. Now the second experiment did by the Faraday and Henry, and the experimental setup is like this. This is a coil connected to the galvanometer. This is a coil. Let us say coil C2. Now I am taking the same type of coil which has less dimensions when compared to the C2. So that coil name is C1, let us say. Now, this is the experimental support for the second experiment did by the Faraday and Henry. This is the coil 1. Initially, it is connected to a power source like a battery, and this setup is initially at a long distance or farthest away from this setup. This setup means this is coil 2, like this we can conclude. This coil 2 is connected to the galvanometer. Now, what the observations of the Faraday and Henry by this experiment, when this coil which is connected to the battery placed near or when it is approaching towards the coil 2, flux will be released like this. You can draw the arrow mark which shows the direction of the flux. So flux means the magnetic field lines which are passing through unit surface area. So that's why when it is drawn like this flux which is releasing from this one. How the magnetic flux is created in the coil 1? See, initially it is connected to the power source. Inside electric field is generated. Whenever the electric field is generated, it produces the magnetic field, and the magnetic field lines transfers from this coil 1 to coil 2 to connect with the opposite poles. So whenever it is approaching like this, then the current direction will be like this in the coil, and this deflection in the coil will be like this. So whenever this coil 1 is moved farthest from the coil 2, then the deflections will be in the opposite direction. So what we can conclude, this is a current carrying coil, and this current carrying coil can produce an induced magnetic field, and this magnetic field can create the disturbance in the secondary coil, and this secondary coil can produce the induced EMF. So this C2 is associated with the magnetic flux. We can say it as a flux linkage also. So this is the experimental support. See, here the flux is traveling towards the C2, the deflections of the galvanometer is towards the right side, left side. So if the C2 is approaching towards the right side, the deflections are also towards the right side. Whenever the north pole of the magnet is placed near to the coil will be acting as a north pole. So that's why it is opposes the same pole. That's why the arrow mark is opposing the north pole of the magnet in the previous experiment. Now they did the other experiment with respect to the same coils by using the tap key also. This will be like this. The third experiment did by the Faraday and Henry is like this. The third one like this. There is a coil. And this coil is connected to the galvanometer initially. Let us say this coil is C2, and there is a C1 coil. Coil C1, C2, connected to the tap key. This coil 1 is connected to the battery and tap key. Coil 2 is simply connected to the galvanometer. Now, if you close the tap key, means after pressing the tap key, we can observe, means that the scientists observed that there is a momentary deflection in the galvanometer, and very next second it is coming to 0 when you pressed the tap key. If you continue to be pressing the tap key, there will be no change in the deflection. Suppose if you leave the tap key, means simply lose the tap key, then also in the opposite direction of the previous, a momentary deflection occurs in the galvanometer and suddenly it is coming to 0. But the deflections of the galvanometer is increasing by putting a conducting rod like iron or copper between the coil. This is very, very important. That means it is a simple example for a conducting rod which is placed inside the coil, acts like a solenoid which can create the uniform magnetic field. This can create the induced EMF. That's why the sensation of the deflection will be more when placed a rod before touching the key. This is also one of the experiments did by the Faraday and Henry. What are the conclusions they observed by these three experiments? And it will be like this. The conclusions are like this. The first experiment, coil, magnet. This coil is connected to the galvanometer. When a magnet is approaching towards the coil, this galvanometer deflection is towards the north pole of the coil, north pole of the magnet. If this is north-south, when it is approaching, this is the deflection. If the poles are interchanged, then the same deflection is occurred in the opposite side of the galvanometer. Then place the magnet at constant position and move the coil towards the magnet. You will see the same effect. No change in the effect. Then try to move both relative to each other or rapid motion like this, a fast and up. then also you will see the same amount of the deflection, there will be no change in the effect, but increase in the galvanometer needle will be faster when they are approaching towards each other. That means magnet which creates the magnetic flux, this flux is nothing but magnetic field lines which are passing through unit surface area of a plane is called magnetic flux. Symbol is 5B. It will be like this also, where B indicates the magnetic field. So, what is the way to increase the deflections? If the deflection is increased, it means more amount of EMF is produced in the coil. There are many ways to increase the EMF produced in the coil. First way, the motion between the speed between the coil and the magnet should be more, means they should be faster up. Second one, by increasing the number of coils also, number of turns in the coils also, we can increase the induced EMF. Whenever a north pole is placed near to the coil, that coil will become north pole. That's why force of repulsion takes place. This will be explained in the Lenz's law. We can see the polarity change also. So this is the first conclusion made by the first experiment. What is the second experiment? This is the coil 1. Coil 2, whatever it may be, one coil is connected to the power source and secondary coil is connected to the galvanometer. Now this coil 2 is connected to the power source which can produce the electric field, and this electric field can produce the magnetic field. Again the flux will disturb the coil, next coil or the nearest coil, then we can see the galvanometer deflections. Here also a relative approach between the two coils increases the galvanometer deflection. It means increases the induced EMF production rate. And one more thing, if you place one coil is stationary, another coil moves up, you will see the same effect. So the relative approach of these two coils will increase the induced EMF again. So same thing will be happened in the third one also, but by placing the iron rod or any aluminum rod, conducting rod, the deflections will be more in amount. So by concludingly, he has given one equation which relates to the EMF and magnetic flux. So what is that equation? d phi b by dt is equal to E. So what is this d phi by b dt? What is this E? What is the sign convention of it? We are going to see now. So the induced EMF, what is the conclusion of the equation? Induced EMF is directly proportional to rate of change in magnetic flux. This is the conclusion made by Faraday and Lenz and Henry to prove this one. So the induced EMF symbol is E, which is directly proportional to rate of change in magnetic flux, means flux, derivation of flux with respect to time, but we are applying the negative sign. What is the meaning of negative sign? Negative sign here, the rate of the induced EMF always opposes the direction of the magnetic flux. Means there are both are opposite in direction. This negative indicates the opposite sign. And if it is for a single coil or single turning of the coil, if there are n number of turnings in the coil, for n turns, the same equation will turn like this. E is proportional to minus n into d d phi b by dt. That means if you want to increase the induced EMF, you should increase the number of turns in the coil. Induced EMF is directly proportional to number of turns in the coil. So we can see like this. And one more thing, what is magnetic flux equation? Phi B is equal to, similar to the electric flux, magnetic field lines passing through unit surface area of the body. So we can write B dot A, it is nothing but BA cos theta. So this is magnetic flux, rate of change in magnetic flux and for n turns, rate of change in magnetic flux for single turns. Now we will see what is the SI unit of magnetic flux. We know that phi B is equal to B dot A, magnetic field into area of cross section. So it is Tesla dot meter square. 1 Tesla dot meter square is equal to Weber. Symbol is capital W, small b. So Weber is the SI unit of magnetic flux. Is the SI unit of magnetic flux. This one be one of the interesting point about the magnetic flux. Now we will see one problem which is related to the magnetic flux and number of turns. The problem statement is like this. A circular coil of radius 10 centimeters which has 500 turns and resistance 2 ohms is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. Okay, it is rotated about its vertical diameter through 180 degrees in 0.25 seconds. Estimate the magnitudes of the EMF and current induced in the coil, where H is equal to horizontal component of the Earth's magnetic field. This is 3 into 10 to the power of minus 5 Tesla. What is flux? Initially, when this coil placed in the Earth's horizontal component of the Earth's magnetic field, from 0 to 180 it is rotated in this time. So, what is the induced EMF d phi b by dt? Means we should find out the change in flux with respect to the given time. So, what is the change in flux? Phi final minus phi initial. So, phi initial is equal to b dot A cos theta, where B is equal to horizontal component of the Earth's magnetic field, 3 into 10 to the power of minus 5 Tesla. Area is equal to circular coil, right? Pi r square, where pi into what is r square? 10 centimeters whole square, it will be 10 power minus 2. Therefore, pi into 10 to the power of minus 2 into cos 0 degrees. So, it will be 3 pi into 10 to the power of minus 7 Webers, because cos 0 is equal to 1. Whenever it is placed in the Earth's horizontal component of the magnetic field, it is rotated through 180 degrees. Now, what is the flux final? Same, 3 into 10 to the power of minus 5. Area, pi into 10 to the power of minus 2 into cos 180. Cos 180 is equal to minus 1. Minus 1 into the whole same thing you will get minus 3 pi into 10 to the power of minus 7 Weber. So what is the change in flux for initial to final? You will get 6 pi into 10 to the power of minus 7, means this is 3 pi into 10 to the power of minus 7 Weber, minus of minus plus 3 pi into 10 to the power of minus 7 Weber. Therefore, change in flux is equal to d phi b is equal to 6 pi into 10 to the power of minus 7 Weber. EMF is equal to N turns into d phi b by dt. Number of turns 500. D phi b 6 pi into 10 to the power of minus 7. dt, time taken 0.25 seconds. So this 0.25 500, it will be 500 into 6 3000 pi into 10 to the power of minus 7 by 0.25 seconds. The answer we will get is equal to 3.8 into 10 to the power of minus 3 volts. This is the EMF when you calculate, where pi is equal to 3.14, 3000 into 3.14 into 10 to the power of minus 7 into divided by 0.25, you will get the answer 3.8 into 10 to the power of minus 3 volts. That is EMF. But not only EMF, we should find out the current also. What is the current EMF by resistance? So the solution will be like this. Therefore, current is equal to I is equal to EMF by resistance. EMF E by R. E value we got 3.8 into 10 to the power of minus 3 volts by resistance 2 ohms. 3.8 1.9. So volt by ohms is equal to amperes. Therefore I is equal to 1.9 into 10 to the power of minus 3 amperes. So this will be the amount of current and this will be the amount of EMF. These values are simply assumed values. The instantaneous values will be different with respect to the speed of the flow of the electrons in the conducting coil. Now we are going to see the Lenz's law and conservation of energy. What is the Lenz's law? Initially, according to Faraday, we have written like this. EMF is equal to minus N into, where N is equal to number of turns, into d phi b by dt. Minus indicates the opposite in direction. That means flux direction is like this. Galvanometer needle direction is also like this. Means they are facing each other with respect to oppositeness. That means the polarity of the EMF is such that it produces a current which opposes change in magnetic flux. The polarity of the EMF is such that it produces a current which opposes the change in magnetic flux. That means whenever a north pole is approaching towards the coil, this coil will become magnetized and that to be acts as a north pole. So this coil become north pole and a north pole is placed near to it, force of repulsion takes place. That's why when a magnet north pole is approaching towards the coil, the orientation of the magnetic field is in anti-clockwise direction. Anti-clockwise direction. When this north pole is moved away, then the orientation of the magnetic field will be in clockwise direction. So we can do like this. Which orients in the anti-clockwise direction. When the magnet is away from the coil, which orients in the clockwise direction. So this is clockwise, this is anti-clockwise. So whatever may be the cases, if they both are under the force of repulsion because of the equally magnetized elements, if the force is between them is repulsion force, a person should do work which can overcome the force of repulsion. Where does the energy which is able to do the work goes? That energy will dissipate in a form of heat inside the coil. That's why, because of this opposite polarity, this coil's resistance will play the key role. That means the person should do work to keep the magnet near to the coil, and the energy spent in doing this work will exhausted in a form of or dissipates in a form of heat. This effect is called heating effect of electricity or heating effect of electromagnetism. So what is the Lenz law? Lenz law is like this, which gives the direction of the polarity of the EMF when a coil is placed in a magnetic field. And this is the directions and orientation of the electrons or the magnetic field when a magnet is approaching or when a magnet is farthest moving. So this is the information. So how can we observe the conservation of energy? If the polarity is same, the energy what we applied is useful to move the ions. If the polarity is different, the energy spent to do the work is exhausted in a form of heat. So conservation means supplied energy is equal to work done by the energy. Means the energy what we are supplying is totally converting to work? No. Some amount of the energy is exhausted in a form of heat. So the amount of energy which is exhausted or dissipated in a form of heat plus work done is equal to supplied energy. So the supplied energy is equal to work done by the energy minus heat. So heat is always a loss. So the sum of these two is equal to the supplied energy. Means there is no possibility for the loss of energy here. Conservation is nothing but loss replaced by the gain. So loss of energy is replaced by the gain of energy. That's why we can say it as a conservation of magnetic energy. So the galvanometer needle always opposes the change in magnetic flux. This change in magnetic flux or opposition in the change in magnetic flux plays the key role to produce the resistance of the coil. So these topics are interrelated to each other. Now the concept is motional electromotive force. The concept is like this. We will take a conducting rod and that rod is moving through in the magnetic field, and what will be the change in the electromagnetic force or electromotive force we are going to see now. For that purpose, take a magnetic material which is in a rectangular shape. Now this is RS. Initially one conductor rod we took and it is placed like this. And this conductor rod is moved towards the RS by crossing the uniform magnetic field. So it is crossed like this. Now this rod is PQ. Here it is moved from here to here. This is the distance travel. Whenever a conducting rod placed here, this whole surface will act like a closed loop. It's completely closed. Means the conductor fully absorbs the electrons and there will be no leakage to the outside. So this PQRS will act like a closed loop. Now, what we can understand in this way, what is magnetic flux? B dot A means field into area. See, the Q is, let us say it is the X. This RS, let us say it is L. So length is X, breadth is L. You can say like that, or we can interchange the parameters also, no problem in it. So we can write area is equal to length into breadth Lx. Therefore, phi b is equal to BLX. Now, EMF is equal to electromotive force is equal to E is equal to minus d phi b by dt. So minus d by dt of phi b is minus BLX. Why minus? The amount of work done to overcome the force of repulsion while it is coming towards the RS segment of the magnet. That's why minus. Therefore, minus into minus plus, we can write BL into dx by dt. Therefore, it is BLV. It is the EMF expression. Now, we will see what is the amount of work done in moving this rod from here to here to overcome or to oppose the direction of magnetic field. So, therefore, work done in moving the rod again is the field is equal to work done is equal to force into displacement. Force is equal to QVB. The displacement is X. So EMF is equal to W by Q, means work done on a unit positive charge. What is W? QVBL by Q. Q get cancelled. This will be BLV. So in any way, any form or any way, we are getting the same equations. So we are taking the length, the distance traveled by them is, let us say L. That L and L get, that Q and Q get cancelled. We will get a BVL. Next one is Lorenz force. So what is Lorenz force? Lorenz force is the minimum amount of force required to separate the electric and magnetic fields, or the minimum amount of force which is required to combine the both the fields. So in combination, Fe is equal to QE, electrostatic force. Fb is equal to Q into V cross B, where velocity and magnetic field both are perpendicular to each other. Therefore, Lorenz force FL is equal to Fe plus Fb, QE plus Q into V cross B. Now Q is common, we can say E plus V cross B. This is the expression for Lorenz force, and we can write this one as Q into E plus VB sin theta. So vector product between V cross B is VB sin theta. So this is the information about the Lorenz force, which is the combination of electrostatic force plus magnetostatic force. So in case of Lorenz force, Q into E plus V cross B, if V is equal to 0, means velocity of the magnetic field is 0. Once a rod which is moved towards the another end of the rod, if that is acting like a closed loop, V is 0. In this case, Lorenz force is equal to QE, nothing but electrostatic force. In case of V is equal to 0. If electric field is 0, then we can say Lorenz force is equal to the QVB. Next one, energy consideration. We know that whenever a rod which is moving towards the magnetic field, it produces an induced EMF, nothing but the current. So the equation of current is equal to, we can write V by R, including Ohm's law. The same law is valid for the, in case of EMF, we can write EMF by internal resistance. So I is equal to E by R. But what is EMF? E is equal to BLV. Therefore, BLV by R is equal to I. What is the force? BIL. I is there, so we are substituting this I value, nothing but equation 1. So from equation 1, F is equal to B into, what is I? BLV into L. We can write it as L also. So B square L into L, L square V by R is equal to force. This is the force due to the magnetic field, length of the conductor, velocity with respect to the radius of the loop. Now, how much is the power dissipated in case of this one? Means the power dissipated when a conducting rod which is moving in the magnetic field to the opposite direction of the magnetic field, or to overcome the magnetic field, power dissipation P is equal to, we can write FV. So let us say this is equation 2. So from equation 2, power is equal to, what is F? B square L square V by R. V is V. So it is V square L square V square by R is equal to power. This is equation 3. But we know that the power and the resistance are directly proportional to each other. That means power is equal to I square R. Now we should convert this whole to the I square into R. So power is equal to, we can write BLV by R whole square into R. Therefore I is equal to, again we are getting BLV by R. So in any way we are going to the conservation of the current. So therefore I square is equal to BLV by R whole square. So I is equal to BLV by R. So this is the proof of the conservation of the electric energy in case of the moving charges. So thus what we can conclude, the mechanical energy spent to move a PQ rod or rod PQ in magnetic field converted to electric field or electrical energy, then to the thermal energy, nothing but the heat dissipation. So this proves the law of conservation of energy in electromagnetic fields. So what we can write, thus the energy spent to move the rod PQ against the magnetic field converted to electrical energy then thermal energy, nothing but the heat dissipation. Heat dissipation. So we can think like this. Now we are going to see an interesting relationship between flux to the charge, like this. What is EMF? d phi b by dt. This is equation 1. Same EMF we can write as IR. This is equation 2. But I is equal to, we can write dq by dt. This one we can write delta phi b by delta t. This is IR, and this one is delta q by delta t. So in any case, just try to compare this I value in this equation. So what is I? dq by dt into R. Just compare the equations 1 and 3. From equations 1 and 3, we can write IR is equal to delta phi b by delta t, where I is equal to delta q by delta t into R is equal to delta phi b by delta t. Delta t can cancel. Therefore, delta q is equal to delta phi b by R. This is the relationship between charge to the magnetic flux. So we can write dq is equal to d phi b by R. This is an interesting relationship between charge to the magnetic flux with respect to the density. That means charge is inversely proportional to the distance between the conductors. Now the problem which is related to the EMF and the length. The problem is like this. The wingspan of an aeroplane is 36 meters. If the plane is flying at 400 kilometers per hour, find the induced EMF between the wings tips and assume the magnetic field P is equal to 4 into 10 to the power of minus 5 Tesla. Because on earth it is 3 into 10 to the power of minus 5 Tesla. The problem is that the plane is at a height. It is not at the horizontal surface. So it is at a height, at altitudes it is moving. So there is a possibility for the change in B. So that's why please check the values. Length of the wing is 36 meters. Plane is flying at 400 kilometers per hour. Means velocity is equal to 400 kmph. We should convert into meters per second. That means 400 into 5 by 18, 9 times, 200 times 2. So 1000 by 9 meters per second. Then what is the B value? 4 into 10 to the power of minus 5 Tesla. Therefore, EMF is equal to E is equal to B LV B. 4 into 10 to the power of minus 5 L 36 V 1000 by 9. 936 4 times 4 4 16, 10 cube 10 power minus 5. It is 16 into 10 to the power of minus 2, approximately 0.16 volts. So this much potential or this much EMF will produce between the wings tips. Next concept is eddy currents. What is the meaning of eddy currents? See, these are the strong magnetic fields or magnetic poles. In between the magnetic poles, with the help of one pivot, one metallic conductor is hanged. Suppose if it is hanged like this, this is the initial arrangement. Now this pivot is hanged like this object. It is a metallic conductor made up of copper, aluminum, iron, whatever it may be. Now cross sectional like this, North pole, South pole, and the rod is oscillating like this. Whenever this metallic conductor placed or crossing in between North and South pole, there is a magnetic flux in between North and South pole. This magnetic flux will produce an induced EMF within this coil. But the direction of the North to South pole of the magnetic field is always from North to South, which creates the slowdown of this metallic conductor. Means this metallic conductor, where it is placed between the North and South pole, it's slow down and again fasten up. Slow down, fasten up. That means this metallic conductor will move like this, like an eddy wave, which is possible in water. When you drop a stone in a steady water or calm water, the waves will produce like this. At one point it is amplitude maximum, very next amplitude is minimum. Like that, this metallic conductor, which is placed between the strong magnetic poles of a field, it will move like a eddy like this. Eddy like means it is first of all decreasing the velocity, next fast enough, decreasing, fast enough. Decreasing means under the influence of magnetic field. Fast enough means it is crossing the magnetic field. While this distortions and unevens, it loses the energy, and this loss of energy will exhaust in a form of heat. These type of currents are called eddy currents. So what is the definition of eddy currents? The change in magnetic flux can produce a current loop in the nearby conductor. And this conductor exhausts the current in a form of heat. These conductors dissipates the current in a form of heat. These type of currents are called eddy currents. This current is called eddy current. The concept of this eddy current was discovered by Foucault. So, a wave-like pattern you can observe in a metallic conductor when it is placed in a north and south pole. When it is approaching to the south pole, when it is near to the south pole, field will be like this, south pole like this. So, the change in magnetic flux alternatively with respect to the pole's strength. This is called eddy currents. So, The formula is M is equal to I into A. Magnetic field intensity is equal to current into area of the conductor. We can reduce the eddy currents. These eddy currents have many uses and some losses also. How to reduce the eddy currents? Reduction or reduce. Reducing the eddy currents. This reducing the way of the eddy currents is helpful in transformers. So if this is the metal core, make holes in a regular order. So through the holes, the magnetic field lines can penetrate. That means the effect of the eddy currents can be minimized. So the first one is making holes to conductor plate. Second one, we can keep an insulating material on the metallic core which is in the direction of magnetic field. Insulating material owning on metallic core in the direction of magnetic field. This is one example. This is one of the way we can keep the insulating material. The insulating material example is lacquer. This type of materials we can wound so which can minimize the eddy currents effect. Insulation means which cannot conduct. That is one example. The third one, what is the reason to do all these things? The heat energy which is dissipated due to the eddy currents is directly proportional to the square of the amount of currents. So how to minimize this? Making the parallel angle. So that one. And one more way, we can make a zigzag order within the metallic core like this. Like this. So through the gaps of this zigzag, the magnetic field waves can penetrate and eddy current strength will be reduced. If these things are not happened or not done with the metallic cores, eddy currents will produce continuously. These eddy currents have many uses. What are the uses of the eddy currents? We will see now. The first use of the eddy current is magnetic braking. Now, all of the trains, many trains which are electrified, means above one transformer is there, that a transformer is connected to the power supply line, okay, then some electromagnetic current will be produced. So, whenever these electric trains which are connected to the power sources which are to the wires of some 20,000 volts or to 30,000 volts, they will produce some electromagnetic fields. Now, these electromagnetic fields will produce induced EMF as well as eddy currents. These eddy currents always try to oppose the motion of the train. So it means there is no pause, means no need of applying the brakes. The train should be stopped. But whenever these electromagnetic fields, eddy currents and induced EMF are playing the key role to move the body, mechanical energy is completely lost. Energy becomes negligible. Because of this mechanical energy negligence or negligible mechanical energy which is played in the train, the braking effect will be smooth. Will be smooth. Why? Already eddy currents are playing to stop the train, opposes the motion of the train. So these eddy currents are trying to oppose the motion of the train. So the induced EMF is keeping the trains in touch with the magnetic needle. So that's why mechanical energy will become negligible. The braking effect will be smooth. This is one of the use of eddy currents. Second one, galvanometer. If you see the galvanometer needle, sometimes this galvanometer needle is connected with a non-conductor source or insulating core. Suppose if it is connected to any power supply, you can see the magnetic effects in the galvanometer needle. The needle will turn to the left side or right side with respect to the applied electric field or magnetic fields. Sometimes maybe it is a time dependent oscillation. Within quick time it comes to the rest quickly. What is the reason? The damping current or nothing but the eddy current which is produced in the core of the galvanometer coil, which keeps the coil or which keeps the needle towards the mean position. So the eddy currents which are produced in the galvanometer coil keeps the galvanometer coil to be in the mean position always. So the eddy currents which keeps the position of the needle at the mean position. This is one of the example in the galvanometer. Third one is induction furnace. This furnace is useful to prepare the alloys. If you want to prepare any alloy of any 2 or 3 metals, the metals won't melt at normal temperature. So we should produce such a huge amount of the temperature to melt the metals and to prepare the alloys again. So it is very difficult to produce those range of temperatures with our natural sources. That's why we are using the induction furnace. We can see in the many showrooms of the vehicles, we can see the induction furnace. So what is the use of furnace? If you see the iron metal, its melting point is almost equal to 2000 degrees Celsius or 1700 to 2000. It is very difficult to produce that much of temperature. Now the metals what we are taking in furnace, they are wounded by the coils. These coils, through these coils, a certain amount of current is passed through. That current is nothing but the eddy current. Eddy current dissipates the heat energy. So whenever the eddy current which is in the coil surrounded by the metals passing through that, which produces the heat energy, because of that heat these metals will be melted. And these molten metals will combine to form an alloy. First the coil. Through the coil eddy currents will be produced, eddy currents will be passed. This will produce the dissipation of heat energy. This heat energy, these metals will be melted. Those molten will becomes an alloy. This is one of the example of induction furnace with the help of eddy currents. Last one, electric meters. So what is electric meter? Now everything is digitalized. If you go to the 10 years or 15 years back, the meters, electric meters always changes the numbers like a petrol bunk reading, and it has a silver coated circular coil which has silver coated almost all 3/4, only 1/4 is with the red. That red is able to identify the number of turns. That coil rotates due to the eddy currents produced in that coil. So whenever you switched on any circuit or any appliance, the heating effect will turns the circular coil which is placed in the electric meter. So with respect to the eddy current, this coil will rotate, and this rotation helps to change the numbers, and we can find out the examiner can find out the number of units consumed within a month or given period. So electric meters are also run with the help of eddy currents. So the eddy currents is helpful to the smoothing effect of magnetic braking in the trains, which is helpful to find out the electric meter reading with the help of the rotation of the circular coil, which is silver coated and red, which is helpful to produce the temperatures of 2000 to 3000 degrees Celsius within the coils or furnace to prepare the alloys, and such like examples we can see with the help of eddy currents.